Hello, good afternoon. Today I will present some conclusions from the T-FORS Horizon Europe project in our effort to develop a real-time forecasting system for traveling ionospheric disturbances. The main objective of the T-FORS project is the development of new validated models able to issue forecasts and alerts for TIDs several hours ahead, exploiting broad range of observations of the solar corona, the interplanetary medium, the magnetosphere, the ionosphere, and the atmosphere. We are using data sources that span at least one solar cycle, and for large-scale TIDs, we mainly base our developments on solar wind characteristics, auroral oval data, and GNSS tech gradients, but also tech detections with the HF interferometry and ionograms and calculated profiles for validation of the results. For medium-scale TIDs, we use D-Trendic tech as drivers, but also for the detection of TIDs. And for the validation, we use ionograms, CDSS data, and features from tech kiograms. The methodology is organized in 3 action lines. For TIDs forecasting classification, we mainly work with machine learning algorithms, and we focus on the cut boost and on the temporal fusion transformers. For medium-scale TIDs, we are developing climatological models, and on top we calculate the effect of dynamic events on medium-scale TID propagation, and under some specific criteria we issue alerts for very dynamic events. And in the bottom row you can see the chain of efforts to test and to even further improve our models using on-ground experiments. Now, more specifically for the large-scale TIDs, we start our development using the chain on events that starts from the auroral oval, and for that we are using IL and IU indices from the image magnetometer array, and GNSS tech gradients from DLR that cover the high to middle European region. For the large-scale detection, we use the HF interferometry method over Digisonde, and more specifically the spectral energy contribution SEC of the detected TIDs, which is used as a classifier for TID activity. These are here are some results where the metrics that we are using are the recall and the precision, and their harmonic mean is the F1 score, which is the overall metric for the performance of the models. The forecast of the occurrence of large-scale TIDs is considered as a binary classification problem, and a predefined threshold theta of the SEC characteristic, which is computed with the HF interferometry method. Here you can see the performance of 3 classifiers. We have the more advanced, which is the TFT classifier with the blue line, and the other more classic classifiers, the FNN and the KNN, and which always performs worse than the TFT. And it's also important to say that the performance drops with the increase of the forecasting horizon. For medium-scale TIDs forecast, we develop the climatology, which is based on the DTEC data over Europe. And the DTEC can catch even variations even less than 1 tech unit, and also short period oscillations. And here in this plot you can see the climatological effect of the solar terminator of medium-scale TIDs over Pruchonice in Czechia. as an example, and the results are for one whole year, 2023. And on the right here, you can see the effect of a geomagnetic storm, which is a dynamic phenomenon that causes medium-scale TID activity that exceeds the climatology, which is defined with a range between the first and the third quartile. And when this happens, we issue an alert. In parallel, we are performing on-ground demonstrations with the Nostradamus over the horizon radar being the transmitting point and the direction finding in Germany to be the receiving point. And in this experiment that was organized in July this year, we have detected a deviation in the azimuth of 26 degrees that was due to TIDs that were correctly forecasted by the FORS models. Now we are now working to build the TID forecasting system, and this system should host big data in databases with data from interplanetary medium, the magnetosphere, the ionosphere, and the atmosphere, and also models that can be very fast executed. And the results are at the moment raw results of medium-scale TID forecasts and large-scale TID forecasts. And we are in the process to transform this raw data to high-level data products. In doing so, we have to consider how this transition will be done, and we have to consider standards, some community standards from the World Meteorological Office through the OSCAR recommendations that have to do with uncertainty, timeliness, coverage quality, and confidence level. Community standards from PITHIA NRF research infrastructure that give us guidelines for the ontology, for the API, and for the future machine learning framework. We also have to consider, as designers and developers of the data products, issues that have to do with the storage interface and cleaning of data, of the latency of data, but also issues that have to do with the accuracy in the horizon, the forecasting horizon, and issues that have to do with data pre-processing and the time of the model execution and the model training. For the end user, we have to consider some general requirements, but also specific requirements that all have to do with the accuracy, forecasting horizon, the design, the format of the data, the availability of the data products in archived and in real-time mode, and the quality indicators, but also the robustness of the IT service. So all these are under development, and we invite you to follow all our developments in our website. Thank you for your attention.